Hello, everyone. Welcome to our second episode of From Local to Global series. Today, we will be with Tomàs PINÓS from Spain, and he will be explaining us about research challenges on rare diseases and glycogen storage diseases. Now, I would like to welcome Professor Tomàs.
Thank you, Leila.
Hello, Professor. Welcome.
It's a pleasure to be here.
Thank you. If you're ready, we can start to your presentation.
Okay, let's see if I do it well, sharing the screen.
Yes, we can see now.
Okay, I put full screen.
Yes.
It's well seen? Yes?
Yes.
Okay,
Now
so
it is yours. Thank you.
thank you, Leila. So the issue of my talk will be research challenges on rare diseases, and I will focus on the family of diseases that I know the best, which is muscle glycogen storage diseases, that I've been studying for the last 13, 14 years. So, but first, before entering to the proper issue of the team, let me start with little two anecdotes that will make it more easy to begin with. You will see here this person here. This person is Claude Bernard. He lived in the 19th century, and when he was young, he was a pharmacist student. And I'm explaining all this because I know that most of you are students. I was a student myself some years ago, and I wasn't sure about my vocation. There were many options out there, and I saw some of my friends that have very clearly in mind what they wanted to do, and it wasn't my case. I was doubting, and I was concerned that could affect my career, or that it was better to have one passion. In the case of Claude Bernard, he studied pharmacy, but it was not his conviction. He wanted to write literature. He wanted to be a writer of theater plays. And in fact, while working on the pharmacy shop, in the backyard, he spent most of the time writing. And that was his passion. And in the end, a friend of the family was a critic of literature. So he wrote one of the plays, reached this critic, a friend of the family, and showed the play. And the critic said, no. You cannot spend your life doing this. You are not going nowhere doing this. And he was really disappointed. And then he had to continue doing pharmacy because he was studying, but his passion was broken. Here on the side, I'm showing one of the plays that it was published after he was dead. Well, Claude Bernard continued what he was studying, pharmacy, and in the end became the discoverer of glycogen. Another thing that was known was for vivisection. Vivisection in the 19th century was understood as doing experiments with live animals. In fact, his family was against that, and he was abandoned by his wife and her daughter due to the experimentation with animals. Here you can see, let me see if I can find the pointer. You can see a painting in which experimentation with animals is shown on a table, probably in the house of Claude Bernard with many friend researchers. Another little anecdote in the field of glycogen, and from that on we will start with the research title of glycogen storage diseases, is this woman here below. This is Gerty Cori. Gerty Cori was also very important in the field of glycogen. He was born in Czech Republic now, the old Austria-Hungary empire. And in the 1920s, she moved to United States with his well-known husband, also a researcher, that was Carl Cori. The anecdote here is that in the US, where they moved to in the 20s, was that they wouldn't allow her to do research on the lab. they said to her husband that you only can do research, you, not your wife. If you do research with your wife, this is going to be un-American. You are not welcome to do research with your wife. So obviously that was very disappointing for her. But in the end, she continued. She pursued her dream that was doing research, and ending being the first woman to win the Nobel Prize of Physiology and Medicine, and the third woman to win a Nobel Prize after Marie Curie. Nowadays, there is a crater that I'm showing here. This is a moon, and there is also a Venus crater called Curie crater. And this is after her, not after her husband. So this was just a little two anecdotes to begin with. So the title was Challenges on Rare Diseases. But what is a rare disease? Well, there is not a single definition. If you see what I've written here in the slide, the definition really varies from country to country. For example, in the United States, it's when a disease affects less than 200,000 people or less than one person affected every 1,500. In Japan, for example, it's the frequency, the prevalence is more or less similar when a disease affects less than one person every 2,500. And in the European Commission decided that is more or less the same numbers, less than one person every 2,000 people. These are what is more or less the numbers for a rare disease, but it varies. Global Genes Projects estimates that more than 300 million persons are affected for a rare disease worldwide. But what about country by country? We just given three numbers of three well-known countries, and here, using this Knowledge Ecologic International database, we have found that this can also be found in Wikipedia, but comes from this database, the numbers for countries, different countries. And you can see that if we could create an average, that would be a disease is considered rare when it affects less than one every 2,000 people. But what about Turkey? I didn't know nothing about Turkey. I do research and I found this published in this database. And rare diseases in Turkey are seen in out of every 16 people, affecting a total of 5 million persons in Turkey. And which are some rare disease facts? The thing is that there are more than 7,000 rare diseases, but 80% of the patients affected of rare diseases only belong to 350. It means that there are more than 6,700 rare diseases that only counts for 20% of the population. What does the population affected by rare diseases, what does it mean? It means that these 6,000, more than 6,000 diseases are very ultra rare. Each disease affects only a very low number of persons. Also, very important is that rare diseases, 50% of the patients are children. In fact, if we go here, we see that rare diseases are responsible of 30%, 35% of the deaths in the first year of life. And also that 30% of the patients will not live to see their 5th birthday. So even though disease by disease might represent a very low prevalence of population, the sum of all diseases, this is not rare. This is very common. But specifically, I said that I'm more familiar with glycogen storage disorders. Which are these family of diseases? This is not a single disease. As I said, it's a family of diseases. There are 17 different glycogen storage disorders. Some are quite common within the rare, and some are very ultra rare. In fact, in one case, there are only 5 patients described worldwide, but we will go to this later on. The whole family of diseases affect between one person every 20,000, 43,000 people. It's really difficult sometimes to provide a prevalence for rare diseases. Very difficult because you have to account that many of these diseases are undiagnosed, misdiagnosed, or based on numbers that are just provisional. In this case, glycogen storage disorders, as many other rare diseases, are inherited It means it has a genetic cause, usually autosomal recessive, and in case of glycogen storage disorders, affect glycogen synthesis, breakdown, or in glycolysis. In the right panel, you can see the glycogen synthesis, glycolysis, and all pathways involved in glycogen synthesis and glycolysis affecting glycogen storage diseases. And you see the Roman numbers in which are pointing to the enzyme and the specific pathway that is affecting these diseases. But this family of diseases, even though they are 17 different, all of them affect mainly or the skeletal muscle or the liver, and in some cases, both. Why? Because glycogen is mainly stored in these two tissues. So when metabolic deficiency of these pathways is altered in glycogen metabolism, these are the two tissues that are going to be more affected. In case of skeletal muscle affection, what it causes is exercise intolerance. And in the liver, when there is affecting the liver, basically affects glucose homeostasis. And we will go in more detail later. As I said, this is a family of diseases. Obviously, I don't want you to pay attention to this in detail to this table. This is just to represent that this is a wide family of diseases. And from those, I'm gonna close this. And from these 17, 12 affects the skeletal muscle, while 5 affects the liver. In terms of diagnosis, if you have a child that is born with a liver disease of glycogen storage, it's easy to detect, or relatively easy to detect. Why? Because glycogen accumulation in the liver will cause hepatomegaly, and this will be quite easily to be detected by a clinician eye. And also touching the stomach, you can touch that there is an enlargement of the stomach due to this liver enlargement. And then the clinician will go to do the blood analysis in which they will see that the liver is affected. And here proceed on. Another different issue, once it's diagnosed, is how to proceed. But liver is very difficult that a liver disease can be not detected. In case of the muscle, is different because muscle exercise intolerance is quite easily to be self-detected for an adult patient. You can see it hurts. You can see that you cannot do exercises that others do. But what about child? Child is a little bit more complicated. But we are talking about glycogen storage diseases. But what is glycogen? As you probably know, glycogen is a polymer of glucose. It's composed by it's composed by glucose linked by alpha 1,4 linkage, and every 8-10 glucoses there is a 1,6 glucose linkage, glycosidic bond, that creates a branch, providing this kind of a structure, very ramificated. This ramification of glycogen is to decrease the osmosis of also the steric occupation of glycogen within the cells and to decrease the steric space within the cell. And it can be organized in different structures. Mainly, the most common structure is this, the beta granule, that it can be seen here in these electrodense dots within the skeletal muscle electronic microscopy image. In the liver is more common the organization of more complex structure like these alpha granules. So glycogen is not an static molecule. It's constantly being synthesized and degraded. As I said, this family of diseases affects mainly the skeletal muscle and the liver. But why are the glucogen 4 in these two tissues? I always imagine the skeletal muscle as a selfish tissue. Why? Because all the energy that it has, all the ATP that glycogen has to provide is for self-consumption. Why self-consumption? Because the main role of the muscle is contraction, movement. It does not provide energy to any other tissue, while liver is altruist. All the energy in form of glycogen that it will provide it is in order to be distributed in form of blood glucose to go to different tissues. For example, the brain can only use glucose for energy, with the exception of ketone bodies, but it cannot use fatty acids. So it's very important that all the glycogen that the liver has is in order to provide glucose to the blood to be distributed to the different tissues. Why? All the glycogen that has the muscle is just for its own usage in terms of energy consumption for muscle contraction. So here I'm going to talk about the paradigmatic glycogen storage disorders of the muscle. And I'm saying paradigmatic because myocardial disease is the one that I'm showing here. Glycogen storage disorder type 5 is the most common metabolic myopathy and also the most common, even though it's difficult to talk about absolute numbers, but let's say it's one of the most common muscle glycogen storage disorder. Okay, what do these patients have in terms of molecular defects? I'm showing here in the left panel, I see, that there is glucose enters to the cell, the muscle cell, and then glucose can have two pathways, or the immediate consumption through glycolysis, or when there is a lot of glucose in the blood, it will be stored in the form of glycogen. When there is deprivation of food, or when we are not eating after a while, you will need to use this glycogen for exercise contraction. And the enzyme that does it, especially when breaking the 1,4-glycosidic bonds, is myophosphorylase. So when genetic mutations of this enzyme provides the deficiency of myophosphorylase, there is glycogen accumulation. So patients cannot use glycogen. And what it causes, the lack of use of glycogen? Two things. One is glycogen accumulation, which means that the muscle fiber cells will have tons of glycogen that will be disrupting the structure of the cells. But the other thing is lack of energy. Where this energy is necessary? Basically in anaerobic conditions. Why? Because in anaerobic conditions, that normally is in intense dynamic exercise or in isometric exercise, and especially at the beginning of exercise, when you begin to move, you have not yet given time to vasodilatation, to make arrive the oxygen to the muscle tissues. So all your conditions are anaerobic. So at the beginning of exercise, or in anaerobic exercise per se, like running, sprint, or isometric exercise like carrying and lifting weights, you rely on glycogen. So if you cannot use glycogen in these conditions, the muscle is going to break. And what the patient feels is like very strong pain at the beginning of exercise or doing these exercises that can be accompanied by rhabdomyolysis. Rhabdomyolysis is what I have just mentioned, that is breaking of the muscle. If you break the muscle, what happens? That all the proteins of the muscle, within the muscle, goes to the blood. And all this huge amount of proteins to the blood will be filtered by the kidney. And then one of the easy ways to detect that you have one of these diseases is when you have urine, that I'm trying to show here. This is what it's called Coke urine, Coca-Cola urine, due to this dark color. This dark color is caused by myoglobin. Myoglobin is one of the proteins that transport oxygen in the muscle, specific of the muscle, has a reddish color. And when it's when the muscle breaks and this protein goes to the blood, it ends in the urine, giving this color. So when there is a patient that is presenting exercise intolerance and reports dark urines, you can begin to suspect that there is muscle break. Another characteristic is second wind. Second wind is that all these patients, and this is pathognomonic. Pathognomonic is when one characteristic of the disease is specific of this disease. No other disease can be defined by this characteristic. In the case of myocardial, is second wind. Second wind is when the patient reports a strong difficulty in beginning an exercise, very strong difficulty. But after 10 minutes, they report that they begin to feel better and they can also begin to perform some kind of exercises that they could not do in the beginning. Why is this for? Because into the muscle, after 10 minutes, you begin to oxidate fatty acids. And also you have given time to produce vasodilatations, arriving oxygen that along with these fatty acids, the oxygen with these fatty acids can produce in the mitochondria oxidation of these fatty acids, producing ATP that can be used by the muscle. Also, after these 10 minutes, you begin to liberate from the liver glucose from either glycogen degradation in the liver or gluconeogenesis. And this is an important thing that I have to clarify. I said that the enzyme that degrades glycogen in the muscle is deficient. But in each particular disease, and sometimes there are isoforms that in each particular disease, for example, in case of myocardial disease, only the enzyme that degrades glycogen in the muscle is affected, but not the enzyme that degrades glycogen in the liver. So this is why part of the second win occurs, because the enzyme that degrades glycogen in the liver liberates glucose and the patient begins to feel better. Obviously, after many periods of doing exercise and breaking muscle, you begin to have muscle wasting, especially in the proximal trunk. In case of rare diseases, and also specifically in case of muscle glycogen storage disorders, and this is also varying a lot from country to country. Normally, if you are diagnosed from a rare disease, you feel alone, you feel rare, you don't know what to do, you have fear. So to be having a hug from patients that tell you that I've been through this, I know what you are being affected from, I can help you, it's very useful for them. So there is this association, which is the International Association for Muscle Glycogen Storage Disease, and they have generated tons of leaflets and information of how to deal with these kind of diseases. It doesn't happen to all different diseases, but if you are affected by one rare disease and you have the luck that there is a strong patient association, that can help you a lot, because all the pathway that these patients have done before you will help you to survive better and to deal better with the disease. And most importantly, I think, that you feel that you are psychologically accompanied by them. Mental issue, even though when you have a physiologic problem, you can feel that it's a minor thing, for them it's not. They have a lot of help when they feel that they are accompanied, that you understand them. So this is a very important thing. And this is very different. And I don't know about Asia, I'm sorry about that. But when you compare Europe from United States, you see strong differences. For example, in Europe, where the health system is most public, patients are basically guided by clinicians. So they don't have this need of association. On the other hand, in the United States, when the health system is most private and the connection between hospitals and the exchange of information is more difficult, because each hospital wants to be independent because it's private and wants its own profit. There, the association of patients is more important, and they are much better organized because they don't have this help from the public system. Okay, we said that we can diagnose myocardial disease observing the glycogen intolerance, also observing this second wind phenomenon, also with the dark urines. And all this is also common for the other muscle glycogen storage disorders. And another important issue for diagnosis is muscle biopsy. Sometimes you cannot get information unless you do a biopsy. And here we observe in the first picture hematoxylineosine staining. These are muscle fibers, and we can see these vacuolations. These vacuolations are characteristic not only for muscle glycogen storage disorders, but is a characteristic of this family of diseases. If we forget this one, let's forget about this one because it's not commonly used, but this is also very, very well used. It's PAS staining. This is a staining of carbohydrates. This is here in this picture what it should look like in a normal patient. Every single cell has carbohydrates, but when there is accumulation, you go from this pale staining to this dark pink staining. And you see this darker stainings coincide with these vacuoles. This is the vacuolization. This subsarcolemical accumulation of glycogen is very characteristic. And also, finally, and this is common to all muscle glycogen storage disorders. What it varies, and it depends from each glycogen storage disorders you are looking at, is the enzyme staining. Here in the last slide, when you are staining for one of the enzymes activity, normally it gets stained, and when there is a lack, it gets dispelled. So from this clinical observation to these histological observations, you can have a guide of what your patient might have. And in the end, obviously, you have to go to genetic testing. Sequencing is the last step, and obviously, it cannot be avoided. Is when, for example, in registry of patients of rare diseases, you cannot include a patient unless it has the specific mutations for a certain genes. So as I said, this family of diseases, especially affecting the muscle, they are having exercise intolerance. So some years ago, medical doctors, when they see one of these patients, what they say to the patient, okay, you have been diagnosed from a disease that is caused by lack of glycogen degradation. So if you do exercise, you will be harmed. You will be harming yourself. In fact, you did exercise before, you broke muscle, all these proteins were to the blood, and look, your urine is dark, so you don't have to move. Well, this has changed during the years. In fact, now the best therapy for these patients, even though is, I know, counterintuitive, the best therapy for these patients is doing exercise, but not in any way. It has to be very controlled exercise. Only in very specialized centers, there are physiotherapists and medical doctors that can tell you how this exercise can be done. In fact, this was very controversial some years ago. Some clinicians said that doing exercise in this kind of diseases was like breathing underwater. And I heard that expression myself, and is how controversial it was. And this is, for example, you see this article that says myocardial paradox. Exercise is a good advice for the exercise intolerance. And why that? Why is that? This was beginning to be said because if you do a really progressive exercise, very well taught by the experts, what you're beginning to do is switch glycogen metabolism to another type of metabolism, that is oxidative metabolism, that is increasing mitochondrial biogenesis and enhancing fatty acid oxidation. So patients that begin to rely on this kind of approach, and not many patients want to follow this, and I will explain that a little bit better now. But the first patients that wanted to trust the clinicians that said, no, you have to do exercise. When they were followed up for 4 years, the increase in the quality of life and the increase in the increase in their wellness was impressive. In fact, there were patients that they could barely walk, and at the end of 4 years follow-up, they could run 10 kilometers. And on the contrary, those patients that followed these initial recommendations of do not move, stay home and sit, they progressively worsened from walking to wheelchair. So this is very important. Do exercise. And also, here I put, because I wanted to show the commercial house, but is what it was shown that giving carbohydrates, even though in the paper it was not said it was Coke, but it could be any energetic drink with sugar, 30, 40 minutes before exercise, it improved it improved a lot the exercise capacity of these patients, because what they could not obtain from glycogen, they could obtain it from blood sugar. But be careful, because if you drink, you have to control yourself first, because an increase of carbohydrates, obviously, if you drink them a lot, you will have obesity problems. And secondly, you have to avoid an a rebuttal of hypoglycemia. If you drink sugar just before well before exercise, at the moment of beginning this exercise, you can have hypoglycemia because you have secreted insulin and all the sugar has been captured. So it has to be really regulated. So the thing is that exercise and some sugar intake improves a lot the quality of life of these patients. But do they like it? No. 50% of the patients do not want to follow these exercise therapy recommendations. They want a pill, they want a pharmac, a drug. And why is that? For different reasons. One is psychological. If you have been hurt at the beginning and you associate a lot the setup of your disease by exercise, this is a psychological burden that some of these patients cannot avoid. We, as theoretically not being diagnosed for nothing, we cannot imagine the hurt that these patients feel, but it must be really strong. Secondly, the effects of exercise are not immediate. It will not be seen in months or even as pills in hours. You're gonna see in years. And thirdly, logistics. As I said, this exercise prescription is not going to be everywhere. If you are talking about rare diseases, normally per country there is one specialized center. If you are living in Ankara and your specialized center is in Istanbul, maybe some people can afford it, but some other people cannot afford it. And you have to travel and you have to go there and they have to teach you. And then you're going to be back at your home. And how can you be sure that once you're back at your home, this will work? And what happens if you don't do it well at home? So due to these psychological, long-term effects, and logistics, economical issues, most of patients do not follow these recommendations. And we are losing them and their quality of life decreases a lot. But as I said, title said challenges, but which challenges? Some of them I've been mentioning. One important is lack of knowledge. As I said, many diseases, are rare, but within rare can be quite common. Other diseases can be ultra rare, affecting just 10 people, 20 people worldwide. So which kind of low knowledge and conclusions can we take from that? How medical doctors around the world can know about these diseases? So when there is a new patient, how can they diagnose this patient? So there is a tons of lack of diagnosis and misdiagnosis. For example, here I'm showing you, let's see if I can point it. Here I'm showing you the diagnosis of myocardial disease in a registry. So we have counted patients, we have introduced patients of myocardial disease in Europe. And in blue, you can see that UK has 93 patients, Spain 65, but Germany and France only 34. Germany, it has 80 million populations, while Spain, for example, has 45. So why are these differences? Logistics, how the health system work, how they exchange information, how the hospitals, they want to prevail the hospital itself. No, this has to be my hospital. I don't share my knowledge to another hospital because our hospital has to be the big one, the one. So it's known that in health systems, when there is a lot of exchange of information, diagnoses are much more easier. Then, diffusion is very important. For example, we did a master class in muscle glucogenosis in Poland. The next month, the first Polish patient was diagnosed. So diffusion of rare diseases is very important and help a lot to diagnosis. One thing is lack of diagnosis, mass diagnosis. For example, in myocardial disease, we know by genetics that we are missing at least between half and 1/3 of patients that remain undiagnosed. Where are these patients? Maybe they are misdiagnosed for chronic fatigue, or fibromyalgia. This is something that we know because genetic data is just calculation, and we know that we should have more patients diagnosed. There are more patients that remain undiagnosed than there. The other thing that is very close related to that is delay on diagnosis. For example, in Spain, we have a registry of 333 patients, and if you see, the symptoms are present in the first decade of life. But when we go to genetic diagnosis, which is intimately related to the final diagnosis of the disease, it occurs in the fourth decade. What does it mean? That these patients go during 30 years from one hospital to the other hospital looking for what is happening to them. Another an important thing is the mild interest of pharma industry. Here, it's kind of controversial because there are some companies that do invest money in rare diseases, but the general message is that because these affect few patients, this has not economic benefit. So why I'm going to invest on that? As I said, there are some exceptions. And in fact, from the 17 glycogen storage diseases, the one that has a very well-known and functions therapeutic drug is Pompe disease, which is type 2. And this is thanks to Genzyme. So for some reason that I still don't know, Genzyme decided to perform and to develop this drug. Probably because when they invest in one rare disease is because they are thinking about the applications of this drug in other more spread diseases. But patients don't care about that. If this drug is going to work on other diseases, okay, better for them. Two antagonic cases. As I said, in the wall of glycogen storage diseases, there are very ultra-rare diseases. For example, here I'm presenting Fernando, is one patient from glycogen storage disease type 15. It's one of the 5 and only 5 patients that have been diagnosed with this disease. Not exactly true, because type 15 can affect the liver. There are more patients affecting the liver, the muscle, but affecting the heart, only 5 patients worldwide. And here he is doing a lot of noise in the social media because his heart can have he can have a heart failure in any moment. But the social security system of the Spanish government that has medical doctors that analyze these kind of cases, they don't know this disease. So they force him to work because as this disease probably they say he is inventing this disease because they don't know this disease, he has to keep working. Which was his action? Making noise in social media, etc., etc. So he put on a trial the social security system in Spain to see, and I'm not sure if this trial is going to an end, but probably they will give him the invalidity for not working anymore. On the other hand, as I said, the most known glycogen storage disease is Pompe disease. Pompe disease affects mainly, it has like a mild disease that affects only adults, but it also has a very strong and important affection in children. And there is this movie with Brendan Fraser and Harrison Ford that talks about the travel of a family and also the medical doctor to cure the disease from a child. We are gaining forward of that because this is a very severe disease. Many kids die before 18 months of age, and with the Genzyme therapy, this is increasingly improving, but is still a bad travel for families, a bad travel. So as I said, exercise therapy is the most useful tool for patients because there is no pill. And we do researchers try to find this pill because either we convince 50% of the patients that they have to do exercise and we are not going to get it because there will be always patients that want to see the immediate cure. So we are trying to do different things. And unfortunately, in the case of myocardial disease, none of them work it. Potential explanations and difficulties is that, again, there is no inversion. For example, in the next slide, not here, let me show you, skip one. In this one, we tried a gene therapy approach for this muscle disease that worked. and it was funded by a pharma company, and it worked in the mice. Obviously, mice is not humans, but it is the first step to continue researching, to continue investigating. But when we were happy, and this was in a collaboration with an Australian group that performed most of the experiments, when we were happy to see that our results is positive and it was promising to continue with humans, it was the logical next step. The study was discontinued. Why? Because the pharma that did invest in the beginning said myocardial disease is not killing as cancer and is not also frequent. It's too rare for drug companies to be interested. So here we have preliminary results that cannot be continued. Of course, we could continue with public fundings, but it's not easy. And it's the continue fight of public research centers in trying to do results, to obtain results to convince pharma industry to invest in patients of rare diseases. Most of these fundings that we obtain is based on, in our case, because we are in the European Union, is based on European public grants, very difficultly from private companies. And as I said, one of the things that works, and I'm continuously saying that because exercise therapy is not only, it's really beneficial for these patients, and this is being spread more and more. In fact, it is said that cardiovascular capacity and cardiovascular and aerobic capacity is a very good indicator of longevity. It is said that it's more than diabetes and other diseases. So cardiovascular capacity due to aerobic training is not only good for patients, it's good for everyone. And here we are reporting all the studies that due to these difficulties in trying to find the pill for this kind of diseases, we are trying to do all the characterization of exercise that we can with these patients, and it works. And it's been extended to other disease patients, like, for example, glycogen storage disease 3 patients. So, but as I said, only 50% of the patients follow these recommendations, and because others do not trust, they want immediate results. They don't want to wait for years. And also, they are afraid that if they go home with a paper that they have just obtained from their specialized center saying you have to do this kind of exercise with these repetitions, they question themselves, I'm going to do it well at home? I'm going to damage myself? And we decided to create an APP that could rescue part of these fears. This is, okay, let's create an APP that could monitorize these patients remotely. We can be in the hospital. For example, you can be a medical doctor in Istanbul, and this patient could be in Ankara or in any other part of the country of Turkey, and be secure that his data, his everyday or her everyday data, physiologic data during this exercise will be live at the moment, recorded and seen by the clinicians. So this is very important because, or we thought it was important because it was a way to give security to these patients and also provide information for everyday's provide information that is not just static pictures. Normally, these patients go to their medical doctors with a frequency of what? Twice a year. So we can only obtain physiologic data from twice a year. Which are the conclusions that we can obtain from twice a year? Which is the dynamic evolution of the disease every day, every month? For example, many of these diseases, especially those that affect skeletal muscle, one of the hidden problems is the heart, because the heart is also muscle. And normally the genes that are expressed in the skeletal muscle, they're also expressed in the heart. Normally the isoforms go together. And if one of these enzymes is missing, we know that the heart, probably because it's a hidden gem, will not be detected. And now we are seeing that the heart is affected. And some of these patients, after a while, they might need a heart transplant, or they might have really heart problems that until now had not been detected. And why had not been detected? Because if you only go twice a year and your main problem is, skeletal muscle, heart problem, skeletal muscle, exercise intolerance, and also they are different specialties. Most of these patients go to neurologists and they will see only the skeletal muscle affection, but not the heart affection. So with more data we gain, we begin to see that heart is affected. So also what we are seeing now is that obtaining data from their heart rate, from the heart evolution every day while doing exercise, it improves. For example, we have followed patients from glycogen storage disease type 3. These are affected by the liver and also the muscle, but now we are seeing that they are also affected by the heart, and their heart ratio is irregular and is increasing with age. And now we are seeing that the heart ratio decreases with exercise. So it's like an adaptation. Again, if we can also include all this data in patient registries, we could have longitudinal picture of these patients. Now, patient registries are becoming increasingly important. Why? For several reasons. One of the reasons is that in case of the rare diseases, the protocols vary a lot country to country. And how to proceed vary a lot country to country because there are many few patients and every country might have its protocols. So one way to put in common what to do, discuss which protocol is best, how to proceed with this patient is to create international registries and share data. Again, sharing data is very important. We should forget about the egos of hospitals, which is the best hospital, which is the best researcher. What it works is sharing data. So creating registries of patients internationally is a good way to see how not only to have these patients being registered, but also to see which is the bias from each country in treating these patients and find solutions for that. And also, it's not the same making diffusion if you have 20 patients, for example, in Netherlands, that if you say, no, we have, in this registry, we have 1,000 patients. When you go to industry or governments with big numbers, they will make you more case than you just go country by country saying, no, we have 10 patients. So we have to sum forces for that. And also, but the problem was that the registries were statical. The data included was just one picture of the time of the visit of the patient. If we could record data from type of exercise they're doing, how they feel, how they improve with the heart ratio, etc., longitudinally, we can create longitudinal data that can predict or can tell us the evolution of the disease. And if we create a huge amount of data, we can then, for a new patient, using artificial intelligence, which is now the approaches that everybody is trying to follow, try to predict which will be the evolution of a new patient presenting certain data based on all the previous data recorded by all patients. And then animal models. Animal models are useful, although sometimes for the general public, controversial tools for studying diseases. We say skeletal muscle diseases, but in fact, we can only study, if we are not using MRI, we can only study histologically, molecularly, in case of patients, one muscle, and generally is the quadriceps vastus lateralis. But in mice, for example, we can do as many biopsies and study as many fiber types as we want. We can see differences between how a disease affects muscle fibers versus comparing aerobic fibers versus glycolytic fibers. For example, we can extract the diaphragm. The diaphragm is not normally a forgotten muscle because it's also a muscle and is involved in respiration. So mice are very important tools for understanding and molecularly understanding disease. So we generated a mouse model of myocardial disease. We got sure that the mice, I don't see my arrow now, yes, did not have any protein of myophosphorylase. And now I'm going to show you videos. I didn't know that when I started with this. I thought that when you modify one gene, automatically the model will reproduce the phenotype. And this is not the case. Normally, from all the animal models created, about 20-30%, only that, after spending 2-3 years creating it, after spending 40,000 euros, now it's getting cheaper, the animal will not reproduce the disease phenotype. So it's really a bet, it's really a risk that you have to take. But in our case, we were lucky. We created a mouse model that not only had the molecular defect, but also the exercise intolerance. Let me show you the videos. This is a treadmill. Here we see a wild-type mice running like a... And here is an electric shock. This is like in a gymnasium, but with the difference of the electric shock. This is not something that we invented, but this is accepted. So the mice is stimulated to run, and the experiment finishes until the mice decides to receive electric shock instead of running. And you count the meters run, and you count the distance run, the time that has been in the treadmill, etc., etc. And this is a wild-type mice. You can hear the sounds of the mice when it receives electric shock. It's a very mild electric shock, though. And you will see now a myocardial mice. It almost cannot get out of the electric shock at the beginning. So huge difference. And we were lucky to have this, that this model was one of those that worked. This is for aerobic exercise. Now I'm going to show you anaerobic exercise, which is more typical of these patients because it's more reliable on glycogen. This is a non-sophisticated wire grip test. You will see this is from home. We hang the mouse here, and it can stains. And the mice are clever enough, if they stay here, to go up to the table that is above. So they don't spend all this time hanging here. While in myocardial mice, they cannot stay there. They hang. They hang, but they fall. They never stay here more than just few seconds. So we were lucky to have this model. In fact, for glycogen storage diseases, we have counted that there are more than 40 different animal models, including cows, including sheep, including dogs, including mice. So now the policies are in reducing the usage of animal models, but still, even though 3D cell cultures, organ on chips, still animal models are very useful. And as what I said, I'm not going to explain this. This is just to say that with animal models, we can study different tissues, compare diaphragm to quadriceps. This is very glycolytic, this is very oxidative, so we have many options to do it here. And for all glycogen storage diseases, all drugs, for example, enzyme replacement therapy that I previously said that work in patients with all this enzyme involvement was first tested in mice, obviously. And also in patients, basically now what we are doing is, as there is still no gene therapy, no pharmacologic drug that works, trying to improve their quality of life, doing exercise tests, and testing different nutritional supplements. Like, as I said, carbohydrates are very important. And it was believed, and you will find in the Patients Association web pages, that they talk about ketogenic diet as an alternative source of energy that will not be accumulated, because if you take carbohydrates, as I said, the other risk is that you synthesize glycogen that later on you will not be able to degrade. So this is a careful issue, but carbohydrates normally work very well and improve the exercise, decrease their damage, so it works. And the rationale of ketogenic diet was that's another different source of energy that would avoid the synthesis of glycogen, where later on you will not be able to degrade it. And patients believe it on that. And you will see many chats, they say it works. But in the end, experimental tests doing very controlled conditions of exercise performance and aerobic analysis showed that acute ketogenic diet supplementation do not improve. And here is one of the studies we are doing with the vice president of the MBG Turkey, Leila, which is here nearby, that introduced me. She is studying, we are beginning to compare which are the difference between Pompe disease and myocardial disease in the diaphragm. The question here is that myocardial, as I said, affects the skeletal muscle, but they do not have respiratory problems. While Pompe disease, patients, one of the main affections is respiratory problems. In fact, they need respiratory assistance. And the curious thing here is that when we analyze diaphragm from mice, it seems that histologically, they have much more glycogen accumulation and at the same time much more damage. So why these mice that do not have respiratory problems and do not die from respiratory issues have such a damaged tissue, while in Pompe disease, this is wild type, this is Pompe. In Pompe disease, which it's known that they die from respiratory issues, it seems to be less affected than myocardial. Well, we don't know yet, but these are some of the studies that we are trying to decipher. These are some microscopic electronic images. I don't know if you are not familiar with it, but this electrodense dot, this is a muscle fiber from diaphragm that is completely destroyed. You see this glycogen accumulation here. You see some mitochondria here with all the cristae, but the structure of the sarcomere is completely destroyed. And this is from myocardial, so there is several damage. We are also beginning to see that in this glycogen accumulation, these electrodense structures, that it looks like a kind of glycogen autophagy specific process, which is also, and you will find it in the literature as glycophagy. Probably most of you have studied autophagy. Autophagy can have several specific forms from different organelles. For example, mitochondrial degradation of using autophagy is mitophagy. And not much is known about glycophagy. There are a lot of articles in the literature, but are more reviews rather than just data. And using these models, we can also begin to decipher how autophagy works. In fact, 90% of the glycogen is all the glycogen is synthesized in the cytoplasm through glycogen synthase. And 90% is degraded in the cytoplasm through glycogen phosphorylase. That enzyme that I said that if it's not working is causing all this glycogen accumulation. But just 10% of the cytoplasm, and we don't know which is the mechanism that says this 10% will go to the lysosome for degradation. This specific selection is not well known, and we will try to understand it a little bit better using these models. See more kind of weird structures like autophagosome-like structures specific for this glycogen accumulation. So when you do a specific, very molecular studies for that, you can say, okay, this is very far from translation. This is very far from translational medicine. How this can affect and improve the quality of life of patients? Well, understanding mechanism, understanding how glycogen degradation works, and these alternative pathways of glycogen degradations can help us to identify therapeutic targets in order to design new drugs that can improve, and obviously reminding that we still do not have a specific pill from this kind of patients. From many liver glycogen storage diseases, gene therapy is becoming an option along with nutritional supplementation. But in muscle glycogen storage diseases, because some of them are very rare, some of them because all the experimentation has been discontinued to the lack of pharma inversion, we still don't have these approaches. So any new identification of potential new therapeutic targets obviously will face these same problems as before, or lack of funding, but it's obviously interesting for trying to see potential different options. Well, this is just immunofluorescence studies that goes in the same way, but I will not go further on that. And I don't know how to say that in Turkish, but I wrote it down and just thank you. Sorry if I've been a little bit chaotic, but I wanted to provide from a very reduction point of view to a more specific point of view. So thank you, Leila, and thank you,
Thank,
everyone.
thank you so much, Professor, for your presentation. And if it's okay for you, we can take some questions that came for you.
Sure.
Okay, the first one is, when you're diagnosing a patient with diseases, why DNA sequencing is the last step? Wouldn't it be easier to first finding the mutation?
Yes. Okay, so basically, you want some direction. Now, every time more in the hospitals, for example, they are including all these exome sequences which target many different genes, but it's kind of benefit inversion, economic inversion. You cannot do an exome to all patients, so you have to be a little bit driven by some indications. So the first thing is the clinical eye. If the medical expert is good, almost instantly we'll know which kind of disease is being the case. So this is has going to have, okay, it has a myopathy, but can be, Duchenne muscle dystrophy, or it can be a metabolic myopathy like glycogen storage disorders. So first of all, the clinical eye, and it will depend of how good the clinical eye is from the medical doctor. The second step is that you have some indication. For example, let's say, okay, I think it's a glycogen storage disorder, but you have 17 different glycogen storage disorders. Okay, affecting muscle, just 12. That's a reduction. But you have, in these 12, you can have several enzymes affected. So as most you can gain from is, let's say, precision in the clinical eye, and also if you can have some help of histology, then the most easy is for defining which specific genes you have to look at the genetic test. Exomes every time are more common, but still you need some definition. You need some reduction of the genes that you are going to look at. I don't know if this answered the question, but I try.
Let's. Second question is, how exactly physical exercise can make a difference on cell function for myocardial patients?
Can you repeat the question because I'm not sure I understood it?
How exactly physical exercise can make a difference on cell function for myocardial patients?
There is a lot of degrees. There are some patients that when you talk with them, because normally when you're a researcher, for example, I'm a molecular researcher, if you don't have contact with patients, this can be just a cold question. You don't see the human problem of that. So when you go to patient associations, you find everything. And you find patients that they say that every morning to get out of bed, it takes them 40 minutes. So it's like a nightmare for them. And then you find other patients that they say that no, for me the only problem is when I have to run to get the bus that is going away. Obviously, this points to a different question. Why this huge variability? One is, as I said, your way of life. If you are trying to be active, even though it hurts or even though you have been told not to move, your quality of life is going to improve a lot. So there is a direct relation between being active and improving your everyday's life. The second is, and we don't know still yet about this, that sure there are modifier genes that some of them are identified that interact with the deficient enzyme and create these divergences between patients.
Okay. The next one. What do you think is missing on myocardial disease diagnosing and treatment?
Diagnosis is the most important for this kind of disease. As I said, this disease is morely affecting quality of life, but is not death threatening. So those patients that have been I don't know, walking from one hospital to the other hospital, some of them they have been told to go to psychiatry because you are inventing it, we don't know this disease, etc., etc., etc. So they are really thankful. And when you talk with patients, you realize that they were very happy when they were first told after 30 years, you have this. That changed a lot. This is the first step. The diagnosis is the most important part. The second is just as today, 15th of April of 2025, once they are diagnosed, what it will create a difference is to be active. To be active, they change a lot. The evolution of disease. If they are kind of depressed and close themselves at home and they don't do anything, they will worsen very, very fast. On the other hand, if they are optimistic and they try to do as a normal life as possible, they will have a good prognosis.
Okay. Another question is how we can stop the pharma industry from thinking about the economics of producing drugs or what can be done about it.
I'm not going to solve this question, so I'm sorry I'm not able to do that. One thing I can tell is that I'm academic, so I work in a public institution, and as you know, public institutions in Europe, we have a lot of difficulties in funding. So a couple of years ago, I decided to do a master to learn how the pharma industry works, a master on health, but there were many of the professors that came from private companies. And one of the first things that shocked me was that they always talk about clients, not patients, clients. And the second thing was that they teach you from the very beginning to make economic numbers. So obviously they are thinking about making your company work, so your economics for keeping your company working and have your workers happy and you don't have to fire anyone. They're money, numbers, numbers, numbers. I don't know how to solve this problem. No idea, no idea, no idea. And I have to deal with it because I'm constantly constantly trying to get fundings from a private company, but it's very difficult.
Yeah, unfortunately. Another question is what do you think about the health of the woman while the pregnancy? Because as it is known, mitochondrial inheritance is from mother to offspring. Can this factor also be considered for new generation?
Sorry, repeat the question again, please.
Yes. What do you think about the health of the woman while the pregnancy?
Mhm.
Because as it is known, mitochondrial inheritance is from mother to
Yes.
offspring. Can this factor also be considered for new generation?
Well, in the mitochondrial myopathies, by sure, this is very important, and this is a complete different issue. Part of the most part of our group study mitochondrial myopathies and inheritance of mitochondrial DNA from the mother. It has to be, of course, considered. Of course, in case of McArdle, which is a mutation that affects nuclear genes. There are many questions that were taboo. For example, we are talking about exercise intolerance. So, giving birth, it's also a process of physical exercise. So it seems to be not affected. In case of a pregnant woman, they can have child normally. There is no case, as far as I know, in the literature that report problems on that. And I said taboo not because of that, because if you go to your patients association pages, and I know I'm getting a little bit out of the question, but I think it's interesting to talk about this. You will find also, as I showed you, McArdle at work, McArdle at school, McArdle at home, recommendations from the patients in these different ambits. And there is one that says that is McArdle at sex. So all the aspects from home to work, school, home, even your sexual life is being considered, especially from patients associations. Maybe not researchers, but yes, from patients associations. And regarding the next generation, Um, Obviously, for rare diseases, consanguinity is a bad thing. It's a bad thing because it increases a lot the frequency of having the rare diseases. But in the case of myocardial, as different to mitochondrial pathology, where especially the mother-child inheritance is very important, I wouldn't make an issue on that. I wouldn't make an issue unless there is a degree of consanguinity within your environment.
Okay. And the last question is quite nice to finish this session about rare disease studies. Do you think Spain is a developed country? Would you recommend students to participate studies in Spanish institutions?
I don't know about other rare diseases, and it also within Spain it varies a lot. For example, I am from Barcelona, and Madrid is the capital. And for many things, Madrid has more money than Barcelona. I don't know if it's the same between Ankara and Istanbul. And I'm sorry mentioning these two cities because they are the ones that I know. But probably the people from Ankara will say, okay, probably Istanbul has more. I don't know. But in the case of research investigation, and not only on rare diseases, Barcelona is becoming a hub of, and we were talking bad about them, but it's becoming a hub of pharma industry. In fact, in the next month, they will open Alexion. Alexion is a division of AstraZeneca specific for rare diseases. So I was saying that there is no inversion for rare diseases, and in fact, this is one of these exceptions. They will open a big hub for rare diseases. I don't know I don't know the final aim of it. I don't know. I don't understand the economic from their point of view, but obviously they have it very calculated. So I would say that cancer is also a big there are a lot of cancer research opportunities here in Barcelona. I would say that more in Madrid. And in rare diseases, in the case of myocardial disease, yes. But I wouldn't, I wouldn't extend that. I wouldn't extend this conclusion that Spain is a good place for rare diseases better. No, I just know myocardial disease. I know that in this case, yes, but I cannot extend that for other rare diseases. But Barcelona is a good place to come because there are a lot of, let's say that in comparison to other cities, uh, it's being creating a hub of biomedicine research. Yes.
Okay, then regarding to this question, I would like to ask one more question. What do you
Sure.
think about rare disease studies in Spain considered other part of Europe, other countries in Europe?
Okay, this is about money. So UK and Germany have more money than Spain has. So it's easier for them to have better research because they have more fundings, they have more resources. So in Europe, UK and Germany, I would say that are the main spots. But if we exclude UK and Germany, even knowing that UK is now not part of the European Union, but let's forget it, just geographically, okay? So I would say that Spain, and I think it's a better place to come in terms of opportunities that I would say France or Italy. I think that we cannot buy anything from them. Even though Spain is considered one of the poor countries in Europe, in terms of research, I think here is a little bit better than France or Italy, for example. But obviously, if you are thinking about coming to Europe and you don't care about the weather of its cold or its sun, UK and Germany are obviously the most important spots in the field of rare diseases and in any field of research.
Thank you. And because at the beginning I was a little bit excited to have you here, can you please shortly explain your background to our audience? Like how you started to studying on rare diseases?
Yes, in fact, my trajectory is a little bit not common because I did my PhD on splicing, alternative splicing. So nothing to do with rare diseases, nothing to do with muscle. I was studying promoter sequences and alternative splicing mechanisms in a gene involved in prostate cancer, so nothing to do. So many people after the PhD, many people in Europe, I'm not just talking about one institution, what they do is move to another country because it's a requirement for further grants. What happened to me is a mixture of professional opportunity and also personal situation. I met my wife, what was going to be later on my wife, in my last year of PhD thesis. So I decided not to move. And then there was an opportunity in the same institution to begin to study muscle and mitochondrial diseases. So I said yes because I wanted to stay at the same place where I had my wife. My wife is a teacher and cannot move to other countries. So I accepted that because there was this opportunity in the same city. And later on, the boss of our laboratory moved to a political position, very important political position. So by accident, I inherited this McArdle disease project. It was just an accident. First, I hated it because I was very happy studying alternative splicing. But then, as I said, like Claude Bernard, finally you like, obviously I'm not Claude Bernard, obviously I'm just an average guy, but it's the same thing that you prefer another thing, but in the end you like what you do. And now is what I'm doing every day and I'm very happy with it. So it was accidental. Everything is accidental. But what I would recommend, especially if personal life is not involved, so that's your own personal choice. Many grants, postdoctoral grants, research grants require Europe, not in Spain, in Europe, require that you do an abroad experience after your PhD thesis. So the best thing is that you do your PhD thesis in one institution and then change and go to a different country. I'm not the good example, but I'm just saying what the grants require you. So most of grants will ask you, okay, how many years abroad do you have? And that gives you a lot of points. So I'm the bad example for that.
Thank you so much for your time and for your sharing your knowledge with us. It was truly an honor for me to have you on MVG Turkey because some of you know, some of you don't, but I am doing an internship with Professor Tomàs. It's been 6 months already, and he's my supervisor. And we're talking about this all the time. So it's truly like super nice experience for me too to have you here. Thank you so much.
Thank you, Leila. Thank you, everyone, and thank you, the organization. And this MBG Turkey is a very good initiative. So keep doing it.
Thank you so much. See you, Professor.
See you.
And thank you so much for your participation to our second episode of From Local to Global. Next time, we will have a professor from France. If you're interested, see you on the next episode. Have a great day.